I welcome you all to this lecture annotation video. So here we will continue the topic of multiplexing. So let's begin. So what we are seeing in here is the elaboration, the next step of frequency division multiplexing. So what we are getting in here is that we are connected to a multiplexer or a mux, which contains 12 voice channels, each of 4 kilohertz, which is combined into a single channel of a 48 kilohertz frequency. So how do we get this value? We have the speed for we have the frequency for a single channel 4 kilohertz, and then we multiply it by 12 because there are 12 voice channels. So we get this 48 kilohertz, which are combined into a group, and this group of 5, each with a different 12 voice channel structure, and then we get this 60 voice channel structure of 240 kilohertz. So how do we get this value? It is very similar to the previous one. We get the speed first, the 48 kilohertz for each channel, and then multiply it with 5 because only 5 are connected to form this supergroup, the single channel supergroup, and then this thing goes on. 10 groups of supergroups, and each with 60 voice channel gives us 600 voice channels, and so on. So this is the analog hierarchy which can be performed using this frequency division multiplexing structure. So I hope you get that. So let's move on forward. Applications of frequency division multiplexing includes, as I have told you before, that it is used in amplitude modulation and frequency modulation radio broadcasting techniques, and it is also used in television broadcasting. Because when we if we do not follow this frequency division multiplexing rule or method, then we will get a problem while transmitting or viewing the televisions. So it is such that when we if we use if we do not use this frequency division multiplexing technique, and all the channels are transmitted using the same frequency, then we might get very overlapping channels, and we might get to see a picture or video of one channel and audio from another channel, and etc. And it was used in the first generation cellular phone, so it was kind of very important at that time. What the smartphones we use is not general purpose right now. That is, it barely resembles the first generation of cellular phone. Now what we have here is a example, a mathematical example. So every bit of mathematical example is your self study, so you have to go through with it. So it's your self study, so I am going to skip it for now. So the next topic, the next type of multiplexing technique is wavelength based. So what do we have here is that we use various signals of various wavelengths, combine them into a single wavelength using the mux, and then we separate the wavelengths and pass them to different channels using the demuxing technique. demultiplexing technique or demux. Now, the more practical example of this wavelength division multiplexing is the rainbow, or the colors that we see every day and everywhere. So these values, violet, orange, etc. So these values of light of every color has different wavelengths. So this is what happens when we use this wavelength technique. That is, we combine these wavelengths to a single transmittable process, and we send them to the receiver. They receive them and process them into separate wavelengths. So let's move on forward. So how do we accomplish joining and separating these wavelengths? We use a prism, of course, because a prism can combine light signals or light waves of different wavelengths, combine them into a single wavelength, and then in the receiver side, in the demultiplexer, we can separate these wavelengths easily using another prism. So let's move on forward. So this is the time division multiplexing technique. So what happens here is that it is the only digital process, and it allows several connections to share high bandwidth of a link, but it uses a time slot to represent or to share the high bandwidth connections. Each connection occupies a portion of time in the link. So how do we accomplish this task? So at first we have here is four input channels in the sender side. This is the sender side and this is the receiver side as usual. So the first slot of time is allocated to this number one input channel, and the second slot is allocated to with or to the second input channel, and the so on, and this sequence repeats itself until all the datas have been passed from the sender to the receiver. This process continues, and while in the demultiplexing state, what happens here is that for the first time slot, this first host or first receiver is only active and other threes are inactive. For the second slot, the second receiver is active and the other receivers are not active. This is what happens in the receiver side. So let's move on forward. So this is a type of a synchronous time division multiplexing. So in synchronous time division multiplexing, the data rate of the link is n times faster and the unit duration is n times shorter. So if we want to process this, we have to be very careful. So this is the total data of channel A. Then we have the total data of channel B, and this is the total data of channel C. So what happens here is that we cut off or we segment this whole data into equal parts using a time slot of t with a duration of t. So data are taken from each line every t seconds. They are used to segregate the data, separate the data, and use them further. So this is what happens right here. And then when we are ready to send via the mask, we combine this structure and formulate a channel, form a channel. And what we have here is that for the sending frame for a duration of t second, this A1 is this portion of the channel, this B1 is the first portion of the channel B, and this C1 is the first portion for the channel C data. These are accumulated together to combine together to form this frame, and these are transmitted towards the receiver. But what do we mean by that the unit duration is n times shorter? That is, we use t seconds for this whole block of A1, but we only use t by 3. This 3 is the value of n here because we have only channels A, B, and C, that is 3 channels. So this is very shorter than it was previously considered, but the data rate is n times faster. So what happens is that during this same time period we are sending 3 datas. So it is 3 times faster in this case. So I hope you get this concept. So let's move on forward. One of the special problems we face in synchronous time division or multiplexing is empty slots. So what happens if, let's say for example, we have 4 channels A, B, C, and D, and if we distribute them or separate them with time t, this is the first, this is the second, and this is the third block of information. So in the first frame, because there is no data for the channel B, this time slot is empty, and this is true for this scenario, the next frame and the next frame also. And because there is a empty slot right here in the channel C, so therefore that portion also remains vacant. So this is very disturbing in while we are trying to send data which is quite faster and reliable. So we should not be using these empty slots. So this is a problem for this kind of time division multiplexing. So how do we manage these problems? So one problem with TDM is how to handle a disparity in input data rates. In all our discussions so far, we assume that the data rates of all inputs lines were the same. So, however, if data rates are not the same, three strategies or a combination of them can be used. We call these three strategies multi-level multiplexing, multi-slot allocation, and pulse stuffing. We will get to see them one by one. So let's begin. This is the multi-level multiplexing. When we have slower channels, the channels which have slow speeds are multiplexing with a higher speed or faster speed channels. What happens? What happens here is that we use these slower channels to we pass these slower channels with a multiplexer, and then we combine them to form a specific to form a speed that matches the other inputs of the channels, and we combine these four channels to form the final output of the mux. So I think you get that, but you should study these descriptions as well. So please be careful. So let's move on forward. So this is the multi-slot uh, concept of multiplexing. So what happens here is that we were concerned with a lower speed and faster speed before. We are combining the lower speed to form a higher speed channel, a single channel of higher speed, and then multiplexing it with the other inputs of the multiplexer. But here we have a higher input which has to be broken down into two different slots so that it matches the speed of the lower inputs. So this is what it happens. So what does it happen is that this 50 kbps is demultiplexed to into two slots of 25 kbps each, and it requires or it kind of behaves like two different inputs for the final marks here. So this is for these inputs, and other inputs are from these channels of similar speed. So I hope you get that. So if you have any questions, please ask me in Google Meet. So this is the pulse stuffing concept of solving our multiplexing issues. So in here, what happens is that if this random or anomalous channel which has uh, slightly less than speed with the other channels. So what we do here is that we add some bits, false bits or pseudo bits, to make this 40 kbps to uniform or maintain this 50 kbps speed. We add some dummy bits and then we use these inputs together to form the output as a whole. So this is what happens in the pulse stuffing scenarios when the inputs channels are not quite integer multiples of each other. So there, if they're not integer multiples, then we use this pulse stuffing method to format them, and they can be used in multiplexing techniques. So this is all about multiplexing, and now this is what we see is digital hierarchy. So we have seen this analog hierarchy based on frequency division multiplexing. It is not actually possible kind of in wavelength division multiplexing. So what we have here is that we use 24 channels, 24 channels each of 64 kbps, and then we multiply them, we get a channel of 1.544 mbps ds1 channel, and then we get 4 channels of ds1 combined to ds2 channels, each of 6.312 mbps megabit or megabits per second, etc. And then we go on, and finally we get this figure, these values. So I hope you get that. So thank you for listening to my lecture annotation video. I hope to see you in next lecture annotation video. So that's it for now. If you have any questions, feel free to ask me in Google Meet. Thank you. See you in next lecture annotation video.